Okay. First, again, I would like to thank especially Jonathan. You worked very hard, really very hard, I know, in the last few weeks to have this meeting so successful. Thank you very much, Jonathan, for taking it on yourself, really. And also Sarah Kedick, which I mentioned yesterday. I think she brought, always when she's here, there is something new happening. The artist in residence, and who knows what are her plans for the future, but something new will happen, I'm sure. So thank you very much, Sarah, for being with us for so long and staying with us. I want today to actually, I shouldn't have been here actually today, because I was very much hoping that Eyal Gal, my student, who did this work in the last 3 years and worked very hard in a field, a new field for me, network science, graph theory, but he was drafted to the army, so I was drafted to give the talk by him. And so this talk will be composed actually of two parts. So the first part it just appeared in Nature Neuroscience 2 days ago. Is a pre-publication. You can see it. And this part was done, as I said, by Eyal Gal. Mickey London was absolutely essential for this work, and it was done with others. You will see. And there is a lot of technicalities there, statistical aspects and so forth, that I'm not going to go into in details today. I just want to give you the general picture, and I hope to make it on time because we are a little bit delayed. And if I will have time, I want to show that that this particular circuit, which is an in silico reconstructed circuit based on biological constraints, can be very useful. This particular circuit can be very useful, and that's what I call a practical use. To explain experimental results, which are otherwise very hard to explain as an experimentalist, because you don't have a handle of all these particular parameters that eventually give rise to the emergent properties that you study, including the SSA that Eli and Nelken mentioned, and other emergent phenomena when you record from many cells. So I want to show you both the circuit and try to analyze the structure hidden within the jungle. And also I want to show you that we can use this circuit, if it is a good one, so to speak, to understand the physiological phenomena. So that's what I'm trying to do today. So we have a jungle. It is a jungle here. We already heard the term jungle, and it's not by coincidence, because it is a jungle. And this is a nice demonstration of the wife of Eyal Gal, who tried to, she's from Bezalel Art School, and she's trying to do a jungle from threads, and we hope that it will be accepted to Nature Neuroscience cover, which will appear next month. So this is one attempt to describe a jungle, but in this jungle, maybe there are these hidden structures, some kind of motifs or structures that are hidden in this jungle, and maybe they are even innate. Maybe you must be born with it, just because you have a particular type of jungle. And this is the question that I would like to really explore, looking at this jungle, which is a reconstructed jungle in our case, but in this case, it's a biological jungle. So of course, as a background, you know that when you look at a high-level connectome, so this is a macro-scale connectome, and you use different techniques. You can see structures, of course. And you can see interesting structures that are different between animals, between mouse and chimpanzee, in terms of global connectivity between regions. And people in the last 10 years, Olaf Spons and others, used graph theory to analyze such structures in terms of connectivity, using this network science, which actually just appeared now as a new journal. There is a new MIT journal called Network Science, to exactly analyze this particular type of structures. And of course, the structure, let's say this complicated structure in our brain, may of course underlie very important functions, maybe language, maybe the fact that this region is connected very heavily to this other region and so forth, multimodal region, enable us to generate symbols, and maybe these other animals that are not so highly connected and so forth cannot generate symbols, who knows. But of course, the structure has a very important meaning, but this is the macro scale, and that's actually easier to analyze, as you understand. we have these technologies, and it's very broad. It's between regions. You can have these axonal projections from one region to another, and you can do a lot of analysis of that sort. So there are many, many papers. I just brought you one, or a comparison, using this, what is called today network science, to analyze the macroconnectomics, and showing that it's highly non-random, that it has particular structures, motifs, and small world, and rich clubs, and all these interesting terms that people are using for network science, including Facebook connectivity and so forth between people and so on. So this is already known for several years, and you also there is a lot of interesting work that I'm learning myself. As I said, I'm new to this field, using this network science to look at particular brains, let's say of schizophrenic brains, and try to compare schizophrenic brain large-scale connectivity to normal, so to speak, brains, and to see whether some of these particular structures, the motifs, or the hubs, or the rich clubs, change due to this particular disease. So as a background, this is a well-established way of looking at structure, at connectivity. But at the level of the microcircuit, we heard today about microcircuits, cortical microcircuit in this case, this jungle as we call it, is there a structure within the jungle? Is it random, typically, or is it far from being random? How do you make sense of the jungle? I just want to mention you that when I speak about the jungle, just to give you numbers, so a jungle in my term, in the term of cortex, is about 100,000 cells within 1 cubic millimeter. So you have a cubic millimeter, 100,000 cells, something on the order of 40 million synapses, 40 million connections within a jungle. So is this connectivity random or not random? Is there a structure or not? Of course, we don't know yet completely, because nobody reconstructed a jungle at a scale of 1 cubic millimeter. There is no reconstructed jungle. This is the connectomics project of Helmstadter, Wilfried Denk, and others. So we have a jungle, and we are trying to understand the jungle, and in order to understand the jungle, we are trying to use some information that is available today. And one of the early descriptions, so to speak, of some structure in the jungle is this important paper that came in 2005, this group of people, including Shklovsky, who started to record from the jungle. So in this case, it's a 4-cell recording in layer 5 from 4 cells in the cat visual cortex. And when they recorded repeatedly many tens of such quartets of cells, they started to show a structure, motifs, much more than expected by random. Okay, so this, as they call it, highly non-random features of synaptic connectivity in local cortical circuit. As I said, this came from very local 4-cell recordings, very, very local, but repetitively enough statistics, hopefully. I'm not sure it was enough. In our hands, you really need a lot of these statistics to really show that this is significant, but anyway, they show that there are some parts, some type of triangular motifs in this case connected together that are much beyond what is expected from a random network. So this was the first paper, and of course the most impressive one until today, this work by Rodrigo Perin and Markham's group, because they had 12 electrodes, so they have much better statistics, on 12 cells simultaneously, and they could do all the connectivity pattern within these 12, and they had about 50 12s like this, 50 times the 12s, and so they have also this connectivity matrix, and they also claim that they find much higher than expected motif structure within this cortical connectivity, highly non-random. Okay, so these are experiments that show that there must be some non-randomness there in the real brain, but we decided to do what also the group of Overlander are doing, is to reconstruct a whole jungle, so to speak, a whole cubic millimeter, or on the order of cubic millimeter. So this is the work of Marcel Overlander, Sackmann, and Jonathan and Chaim are working with them, and so this is the whisker system, and they do these in silico reconstructions. I don't want to go into the detail about how exactly you reconstruct, because each group has a different way of putting things together and reconstructing a circuit. I'll go very fast about what we did, Henry and myself and Blue Brain Project did, in order to reconstruct, but the idea is the same, to put different cell types, different layers with the correct amount of cells, and decide on connectivity under some biological constraint, and eventually get the jungle. But the jungle now is in the computer. It's a pure computer jungle, yes?
But is it more correct to say construct than reconstruct, because it's not a real connectivity?
No. It's not a real connectivity, but that's
constructed connectivity which has similar, perhaps.
Exactly. So you take what you know. I'll show you in a second what we did. You take what you know, and that's exactly what they do with Sackman Oberlander. They take what they know about cell types and location of the cell bodies, layer 5 and layer 3, and numbers and so on, and they assume something about connectivity. And again, I don't, sorry?
It's an estimate of connectivity.
It's an estimate, it's an estimate, yeah.
Reconstruction of the real connectivity from one another.
Yeah, it's a reconstructed.
Reconstruction.
Sorry, say it again. It's an in silico reconstruction, which hopefully is an estimate of reality. Hopefully, but I want to show you that when you reconstruct such a thing, even if it's not directly biology, I want to say that there should be some general rules. Doesn't matter what rule you are using. There should be some general motifs or some general structure that emerge just because you use neurons. Just because you have structure, and you go to the jungle and you make these cells kiss each other from axon to dendrite, when they kiss each other enough times, there are emergent structures. Doesn't matter what you assume. Almost, I think. Maybe I said it too strongly, but we'll see. So you're right. It's a reconstructed jungle based on what we know about biology. So you have to remember, of course, that neurons have structure, and there are different types of neurons, and there are different layers, and you're trying to put things together digitally, so to speak, into this particular volume, and try to see if there's some emergent structure just because you put things together and make them, as I said, kiss each other, hug each other, like Michal Rovner liked to say yesterday. Okay, so I want to remind you that these cells have a structure. Each individual neuron, let's say layer 5 pyramidal cell, has a structure. There is the apical tree, there is the basal tree, and there is the axonal tree, the green tree, and this green tree is going to the left, and this other green tree is going to the right, and so there are structures, these are trees, and there are also variability within a structure. So this cloud that you see around, is the cloud of many cells of this particular morphological type, put one on top of the other. So Henry Markham has, I think, about 100 or maybe more reconstructed layer 5 thick tufted pyramidal cell of this particular morphological type. So when you put them together, you see there is a variability of the structure. So yes, but these are the building blocks of this circuit. So you put all these different things together, taking into account also the cloud, so to speak, the dendritic cloud and the axonal cloud into your reconstructions. This is one aspect, and we know today that there is on the order of 50, maybe 60 morphological types at the different layers and so forth, without going into detail. This is a Cell paper that was published by Markham in 2015. So there is a whole process, Yoram, as we said, that you reconstruct it, as Marcel Oberlander and his team are doing. You take the cell types, you decide on a volume, you can call it microcircle, because this is about a third of a millimeter, and this is about 2 millimeter high, so it's about half a cubic millimeter or something like that, and you put cells together morphologically, just put them in the correct numbers, and soon you will connect them. But also remember, in this case, so in the case of Henry Markham, it's actually the most completed reconstructed in silico, in a sense that not only you put a different type of cell, the 55 types of cells in the correct numbers and so forth, as much as we know, but you also put the physiological properties of each individual cell type. So we know there are 55 morphological types, and there are about 11 electrophysiological types. Some of them fire regularly and so forth. So you put the cell type, also electrical cell types in the correct location and type, and you also put the synaptic dynamics and strength of synapses. So this is the most available reconstructed in silico circuit available today for the type of analysis that I want to discuss. So I don't want to go into the fine details about how do you exactly reconstruct each one of them, and especially, of course, the most important thing is, of course, how do you connect them? What are the rules of connectivity? So these two groups that I mentioned, that are the only groups today that are really trying to build a whole circuit, are using different rules, and there are several steps of these rules. Again, I don't want to go into the details, but when you put all this jungle together, there are too many axons touching too many dendrites, so to speak. They are too close in terms of capability of putative synapses, much more than actually exist. That is an interesting comment, that you have about maybe 40 times more possible synapses in terms of distance between axons and dendrites. So we have a criterion for a putative synapse. 1 micrometer distance could become a synapse if there is a spine there or not. But you physically have much less synapses than you could have synapses. So this is taken into account. So there is a whole process of algorithm, and there is a new paper that came out exactly explaining the whole process of building the connectivity. I'm talking now about the connectivity. One second, just to finish this one sentence. The most important difference actually between the two groups in terms of the connectivity build-up is this part, because we know that cells in the cortex, from biology, we know that pyramidal cells, when, for example, pyramidal cells, when they make contact with each other, they make multiple contacts, always. So on average, for example, from layer 5 to layer 5, you get an average of 5 contacts per axon. So if I'm an axon connecting to you, I make 5 contacts. If I'm inhibitory axon, let's say from basket cells, connected to a pyramidal cell, I make 12 contacts. So we never have one contact. There is no one contact, because there is no one contact in biology, almost never. There is a little bit of it, but this is the distribution of connectivity in this particular case. So this is taken into account when you build it, because you want to also preserve the distribution of number of connections between pairs. And it's never one.
So you mean it's not Poissonian?
It's not Poissonian. Yeah, that's the Poissonian case, and that's after the set of algorithms. It looks like Gaussian, so to speak. So there is this average of 5 contacts per this. It's one pair. Yeah. I'll show you in a sec. Sorry, right?
Yeah. So I thought Peter's rule said that the number of potential synapses is a factor of 5 more than the actual number. And now you're saying it's a factor of 40 more. Is that
40 more.
So the Peter's rule is wrong, or?
Oh, the whole Peter rule is wrong, and Peter himself said that he was wrong.
Okay.
So Peter rule is something we don't use anymore. The word Peter, not Peter, and not Peter later.
No, it's done. But that's done.
Peter rule is not considered anymore, especially after the work of Liftman recent reconstruction, trying to say something that Peter himself did not say. But I don't want to go into Peter. But
you are using, and everybody's using Peter's rule, the form of Peter's rule. I mean, come on.
yeah, well, I mean, the beginning is, so to speak, Peter rule. Of course, you need the axon to be close to a dendrite in order to maybe make a synapse. That you can call it a what? And then you do the pruning. I really don't want to go into the whole, because I want to go into the emergent structures. I don't want to really go into the details that were already published in 2000.
I'm just going to, what we need to know is how much of your results depend on the top part, which is true, and the bottom part, which is made up.
The top part,
those reconstructions, those are real neurons.
Yeah.
Right? But the bottom, the rules by which you get the factor of 40 reduction, you made up.
Absolutely. I made up.
And I made up too. It just made us different.
Yeah. I mean, we all made it up.
Yeah.
As Yoram, I think,
but
wanted to.
But then we need a measure of, when we get a result, how much
of this particular assumption is
depends on what you made up.
Yeah, I agree. We will discuss. Absolutely. We should discuss it. Absolutely. I'm just saying that we are trying, at least from what we know today, until there will be this courageous event within 10 years that we shall have a whole circuit, and that there will be no assumptions anymore, and we shall have the whole circuit built, and we shall see what's happening in the circuit. This is what we can do today, and we should certainly be careful about the results. How do they depend on the assumption? No question about that.
But I want to go back to per millimeter.
That's one of the constraints, yes. No, yes, one of the constraints.
And you're saying this is 40 times larger than the number of connections per millimeter? Is this the...
No,
Factor of 4.
Yes, in the reconstruction, if you count, so to speak, the bouton,
Yeah, I'm just
the
asking
abstract
connections.
bouton.
I'm
Yes.
asking about photons per millimeter. There are 4, you're saying here, and there are 0.1 connections per millimeter. Is this
Yes.
the discrepancy?
Yes.
Is this the factor 4?
Yes.
Okay, but the fact that there are 4 photons per millimeter is an anatomical thing that can be measured.
It is measured, yes. I'm saying that because there is a discrepancy.
So there is no discrepancy. So this is both of them are anatomical facts.
The anatomical fact is that there is this number of bouton per unit length of axon. So every 4 micron there is a bouton, let's say, in reality.
Okay.
Every 4, and you get from the connectivity. If there was this connectivity, you would get much more boutons.
No, that's something else. But I'm saying there is a fact.
Yes. That's why we know that we are making this.
And 0.4. So the 4 bouton per millimeter is a direct, straightforward anatomical fact.
Exactly.
It's not part of the in silico reconstruction.
No, it's not part of it. It's the target. It's the constraint. So let me show it. I'll come back here. I'll just try to say. So there are these constraints. There is this measured bouton density. This is measured in the biology. Actually, for each cell type there are differences. You can see these are the cell types that were measured experimentally. I'm talking about experimentally measured cell types, and this is the bouton density measured experimentally. And this is the bouton types measured in silico after we pruned enough in order to say that we are close to biology for each cell type. So before it was much more dense bouton than we wanted, and then we had to prune through this process. We, say they, and this is Markram's work, they had to prune until they got this matching between the bouton density in the biology to the bouton density in the in silico. So this is one constraint, and there are these other constraints. Again, I don't want to go to it because this is just the building. This is a validation. So this one way to validate is that there is a matching between EPSP size as much as was measured. You see this number of synapses per connection, which is on average 5 for excitatory cells and on average 12 for inhibitory cells, and all these things. So, but let me go on because really I want to go to the new thing, to the jungle. So we built a jungle. You may trust the jungle or not trust the jungle. As I said, we don't know if the jungle is trustworthy, but it depends on our assumptions, but at least we believe that we are close to reality, and I'll show you that we are in some sense, and maybe not in another sense, but I don't know until I will have the real biology reconstructed. So this is the jungle, here is the jungle, this is the number of cells, this is the number of synapses, and we can have now the connectivity matrices, number of connection connectivity, contacts, number of synapses, and we also have synaptic conductance matrix, which I'm not going to speak about, but it's part of this Nature Neuroscience paper. So we can start to analyze the circuit. The immediate thing is to try to see the in degree versus the probability to get this in degree. So this is the number of presynaptic cells connecting to you, and this is the number of postsynaptic cells that you talk to. And you can see that this is a long tail distribution, and this is what is expected from random network with the same average probability for connectivity. So this is what are known to be hubs. So you see that this network has a huge amount, so to speak, or some cells that really receive much more than randomly expected from a random network, a Herder-Schwenny random network. Actually, in this paper, we have many types of randomness, and I don't have time to go into this. Distance-dependent randomness and other aspects of randomness that I'm just showing you. The most simple random network.
In a random network, you expect a Poisson distribution.
So this is so this is what is expected. So almost Gaussian in this particular case with this average connectivity which we have in the circuit. But you see that in the real circuit you have this one, but this is actually not surprising that you would expect to get it. Actually, okay. Actually, of course, when you get it, because you have the circuit, you can say who are the hubs. So you define a hub, let's say from 800 in degrees or something like that. You will call it a hub. This is a cell that receives a lot. Other cells sends a lot. And we can say who are the hub cells. So layer 5 thick tufted are the in hubs. They receive a lot of inputs. Layer 4 are pyramidal cells, the out hubs, and so forth. Interestingly, they are not the same cells. The in hubs and the out hubs are not the same cells in this circuit. They are not the same. These are typically, the in hubs are typically this type of cells. The out hubs are typically this type of cell. There is a minimal overlap between this type of cells. But this is easy to explain. One second, just to complete. This is easy to explain. So I'm jumping here, and I'm saying that, of course, if you have larger dendritic tree, if a cell has a larger dendritic tree, it probably will be a bigger in-hub, because there is a larger probability to get an input, because you have a larger dendritic tree. If you have a larger axonal tree, then you are probably making more connections to everybody who wants to listen to you. So that's what we show here. We cannot do it on the average. We cannot see it directly when we take all the population, but when we take cell type population, let's say this cell type population, and we plot the total dendritic length versus the in degree and so forth, or out degree, we see a good correlation between dendritic length and the in degree, and between axonal length and the out degree. So this is not surprising, but it's certainly not a random network, just because you have different cell types. Some trees are small, some trees are big, they are not identical in reality. I mean, these are real cells, yes, that were put inside. This does not depend on assumption. This is really general. I mean, as much as we know, you have a bigger dendrite, you have more synapses. And there is a huge variability of length of dendrite, so it cannot be random per definition, so to speak, almost. Also, oh sorry, there was a question.
Because you are limited in the size then.
In the what? Sorry, how much time? Because I don't remember when I started.
10 minutes. I told you.
10 minutes? You told me?
7 minutes.
7 minutes. Sorry.
You're limited in the number of connections you can find because you're limited in the size of your reconstructed. So your distribution is actually cut off.
Okay,
But
that's a very good point. I did mention that we are using, actually, I don't know if you remember, but our circuit, the jungle, is built from hexagon, and so actually this hexagon is connected to other 6 hexagons, and they are connected between other in order to avoid boundary conditions. So you also get inputs from the surrounding. So we count the synapses not only within, because there could be a boundary problem at the edge of cells that are not receiving synapses because they are at the edge. But we avoid this edge problem because we also added the rest. But of course, this is only within the circuit. Could be, of course, synapses, and there are, of course, synapses coming from elsewhere, and this we don't count because we don't know it. Okay, so.
Can you tell what type of distribution?
Sorry?
There are many long chains. Can you tell which long chains is this?
Which
Distribution, can you fit back to distribution and you can tell?
we speak about it, not now, we speak about this in the paper. It's a full discussion, but I just want to highlight really the essence, because I want also to go to the other part. I just want to show you that, for example, if you make a statistical measure about rich club means that a hub will tend to make a connection with another hub more than expected by chance. So a hub, I'm rich, I tend to have a rich friend. Yes? This is shown here, so hubs really makes much more than expected from just random network. Again, I don't want to go now into the statistics, I just want to show you
Direct connection.
direct connection. Yeah, direct connection. So if I'm a hub of a certain type, I'm making if I'm a hub, so these are the hubs, I define hub from here, you see these hubs tend to connect to each other, and they are very strongly friends. So rich people like other rich people, and also rich cells like rich cells. And we don't understand it yet. You see, the thing is that, of course, you want to use the circuit even if it's not a correct circuit, you want to understand the emergent property of the circuit. This we don't completely yet understand why these switch hubs why hubs like to talk to other hubs. We have ideas, we now analyze it, but I don't want to go into it. There are also other aspects that we understand better. For example, it seems as on the face of it, if you just look at random network and you ask what is the probability to get reciprocity, it seems on the face of it that you get hyper-reciprocity of the different cell types, because this is what expected theoretically just by multiplying the probability to make a connection, and you seems to get more, but apparently if you take distance dependency,
It's more than preferential attachment. Is it just the
No, I mean if it was just, just random network with
No,
one...
not random.
No, it's not. That's what I'm...
Preferential attachment means that I like to connect to those who are already connected to.
But we understand in this case why it happens. It happens because of distance dependence. Connectivity has a distance dependency. That's what happens in the circuit. Actually, that's what also happens in the biology, as much as we know from people who recorded the probability to make connection as a function of distance. And if you take this into your random network reference and all this...
It's not random. I'm talking about power loss.
Yeah, it's not. I'm saying it's not random. There is a distance.
It's not random. NS rating and power loss are different.
I'm saying it's...
So you are saying if you take into account the distance dependence of
the super reciprocity disappear. That's what we show here. But again, I don't have time. I really want to show you some nice things. I already show you some fantastic things, but I want to show you some additional fantastic things, is things like that. You see, these are the results from the experiments that I mentioned before. This overexpression of these red motifs that I showed you before. This is experimental result. These are the results from analyzing triangular motifs, all these motifs in the circuit. This we did not assume in advance, of course. I didn't assume when we built this that there will be motifs at all. I didn't assume anything. I assumed what we assumed to build it, but this was not assumed. So we were very happy to see this extreme overexpression. Really, this is statistically very, very, very overexpression of this particular set of motifs that were also experimentally overexpressed. This is also recently was measured between inhibitory cells. This particular cell's triangular connectivity likes to be connected. We now understand why. When you build a circuit, and I think it doesn't matter how you build it actually, you will have this overexpression of these motifs. But again, I don't have much time. These transitive motifs will tend to be more apparent than expected from random network.
Again, when you say random network, what exactly?
So we have Erdős-Renyi, the regular, the simple, the most basic, one. This is the one reference. We have distance dependent on top of the Erdős-Renyi, and we have the third one. Again, I didn't want to go into all these details. So we have these different types of statistical references to compare our actual measures, and in all these three cases that you will see in the paper, we get overexpression. So what I show you is now, at least for the three types of random networks that we take, we get this, besides the reciprocity. The reciprocity disappear, as I said before, the reciprocity disappear when we added distance dependence.
These motifs don't disappear.
No, these motifs don't disappear.
And you are saying they must be there.
Yes, I think.
So why they are nothing if why they don't exist in this random network if they must be there? What is the difference?
What is a random here?
Yeah, you are saying they must be there, but
Random, you're talking about random connections. Erdős-Renyi with some probability.
Yeah, they are not in the random network. So maybe I missaid. They don't have in the random network. They don't exist.
Right.
So because this is our reference, they don't exist.
So why they exist? You are saying, but you understand why they exist in your net.
Yes, I understand, but that's what I don't.
Oh, okay.
I have to tell you about the direction of axon, and I have to tell you about the direction of dendrite, and I have to explain to you why this particular direction makes these motifs. But I don't want to do that now because I really am late.
3 minutes.
3 minutes, and I wanted to show you last thing that this is the small world. This topology that we built as a small world topology. I don't want now to go into this, what is exactly small world, but just to tell you something that you will be happy to hear, that on average the distance between two any neuron A and any neuron B that you take, on average, the distance between two neurons in this 40 million synapses jungle is 2.5 neurons, synapses between any two neurons. So there is a measure for small world. It's not only this shortest path, because this is expected from random network, this 2.5. So this is what expected from random network, and that's what we get in terms of path length, but we get more clustering than expected from random network, and that's why it is a small world network. Again, without going into the details, the nice thing here is that we now develop, due to Mickey London, Peter Latham ideas, a new measure for small worldness. So the small worldness is a topological measure, but now in this paper, I think it was accepted to Nature Neuroscience, especially because of this new measure, again inspired by Mickey, is what we call the functional small world. So if there is a spike in neuron A, what is the effect of neuron B in this network? This is like a multiplication of probability to generate a spike in the network. So we have a complete new measure that I didn't bring here mathematically to really measure the effective distance. What is the probability the spike here will affect the probability to have a spike there, and how small network it is functionally, not only in terms of distance, and also taking into account that there are inhibitory synapses in between maybe, so they will change site, but I don't want to go into it. So I'm very proud because yesterday we published the paper, or 2 days ago actually, and we already have many people that like us in this Twitter. So this is good, and this is what I wanted to say here. So I think we found structures. I know that we found structure. I think some of this structure must be there. Really, they must be there because of the structure of dendrites and axons. But we are trying to understand that, and now we are of course going into something that is completely new to me. Of course, again, is what is the meaning of this structure? Let's say that we believe that there are these hubs, and there are rich clubs, and there are motifs, and there is small world. What is the functional meaning of it? What is the functional meaning that this is not a random network, and it has these properties? So of course there is a lot of work about motifs, functional aspect of motifs. I'm reading the literature, trying to understand what can we learn from other literature on genetical motifs and so forth. How can we implement this into our network to understand why are we born? Because I really believe that we are reborn. We are born with these motifs. We are born with these structures, I think, but we shall wait for the reconstruction, and then they must maybe have some significance, or maybe not. We shall see. I want to also show you another practical use very fast, because I really believe in that. I think you can use, if it's a good circuit, we can use it to understand physiological phenomena. Because people record, with electrodes, and they record things, but we can use the same circuit. So here is what Eli mentioned, this stimulus-specific adaptation. We shall work with Eli. He's not yet involved deep into it, although we already started to discuss with him. So this is an experimental result which you just saw about the deviant, much larger deviant than the one that is repeating a lot. There are many papers about this surprise. Tuck, 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 tuck. The cell is very happy to the tuck, and you are too. And tuck, tuck, tuck. Surprise. What is the origin of this surprise? Do we have surprises in our circuit? So we take our circuit, and this is the work of Oren Amsalem, who is sitting back there. And so we take our circuit, and we take the tonotopic structure of the auditory cortex. This is about the size of our circuit, which is here. So you see that it covers a range of tonotopy. And we are now doing a simulation. So this is the thalamus. These are axons, 300 axons coming from the thalamus, something like that. There is this tonotopy in the thalamus. So this cell responds to this frequency from the thalamus. These are axons coming up. These are axons coming up here. And this is axon coming that are sensitive to this. So we can now simulate a sound into our circuit. You see, so this is, let's say, an axon coming in. We know actually the distribution of thalamic axons going into the circuit from this side and from this side. And so we can really simulate and ask, do we get the property of this SSA?
SSA is not a property of the activity, not the connectivity.
First of all, we want to see if the circuit replicates what we measured.
How is it connected to connectivity?
What?
It's a temporal property.
I'll show you. So first of all, the answer is yes. You just take the circuit, you give it a sound. This is the receptive field of a particular axon. You give it a particular sound. All the axons respond to this particular sound according to their tuning curve, and there is a response. And this is something that you saw before, so this is a response of the circuit. This is now the circuit response to sound. Very close to experimental results. So we are very happy because we replicate.
Do you have adaptation in your dynamics?
Sorry?
Do you have any kind of adaptation in your
Of course. 1 second. We have everything that we know. Of course, synapses.
You're out of time.
And
sorry.
so just to say, synapses are adaptive of some cell types. They are there. But is it adaptation? So of course, the regular answer is yes. It is due to adaptation. So this is what the measure that Eddie Nelson mentioned before. You can see that you have this in some layers. You have more of this measure, and you kill the depression between synapses. So typically, the most used explanation is the synaptic depression. That is the cause of this SSA. We kill the depression. We lose a little bit of the SSA, but not completely. And of course, when we so we have adaptation, synaptic adaptation. We can destroy. Now I can control any parameter. I can destroy the adaptation as I did here in the model, but still I get this property. So it's not only adaptation, but I can now destroy I can destroy the depression of the synapse. I can destroy synaptic depression, and so all synapses are not depressed now. I still get this property. I can destroy the adaptation of the spikes. I destroy the phenomena. I can do the reverse. I can destroy the adaptation of the spikes and not the depression of the synapse. I can destroy the connection within the network. So now we start to understand why this network behaves as it is. So I think this is now a wonderful tool. And any experimentalist basically should take this tool and try to understand his or her result using this tool. The only problem with this tool is it's heavy. You need a supercomputer. So we are now developing a new method to reduce the complexity, make the thing run much faster. So every lab will have its own circuit to match, to try to understand the experimental results. So thank you very much.